This unit is called modern physics, as opposed to classical physics or Newtonian mechanics. Usually, modern physics refers to branches of physics developed from early 20th century onward. Classical physics usually concerns events we would normally observe. For example, a baseball or a car that is moving at speeds much slower than the speed of light. Modern physics includes relativity and quantum mechanics, which deal with objects with speeds close to the speed of light, and the very small, such as atoms or even smaller particles. Relativity is not in the AP Physics B curriculum, so we will start with the discovery of electrons. In the late 19th century, studies were done on cathode ray tubes. A cathode ray tube is an evacuated glass tube with a metal cathode and a metal anode. The tube is coated with fluorescent material. When the cathode and anode are connected to a high voltage, a glowing spot can be seen at the end of the tube. And when the tube contains certain types of rarefied gas, a glowing ray can be seen. Because this ray comes out of the cathode, it is called a cathode ray. Scientists conducted studies with cathode ray tubes. For example, when a set of charged plates were added, with the top plate being positively charged and the bottom plate negatively charged, the cathode ray would deflect upward. From this observation, what can you say about the cathode rays? They act like negatively charged particles. Then in 1897, J.J. Thomson designed experiments to measure the charge-to-mass ratio of cathode rays. His third experiment used a lamp setup like this. Cathode rays from the cathode pass through a slit in the anode into a bell jar with rarefied gas. He could measure how much the rays get bent by a magnetic field and the speed of the rays by photographing the path of the rays against a ruled glass plate. One way to find the E/m ratio is to apply only a magnetic field perpendicular to the velocity of the rays, so the rays do circular motion. Therefore, we can write net force equals to ma. Since there is only magnetic field, there is only magnetic force acting on the charge, and that will be QVB, because B is perpendicular to V, so the sine, the angle between V and B is 1. And because the particle is going to do circular motion, the acceleration will be V squared over R. Therefore, we get the charge to mass ratio Q/m, which will be E/m for the electron, would equal to V/BR. Then he could add an electric field in this region to make the rays go straight undeflected. This means there will be an electric force and a magnetic force acting on the particle, and those two forces must be equal and opposite so they can cancel, which means the electric force will be Q times E, and the magnetic force will be QVB, and the Q's cancel. That means we get the speed of the particle to be E/B. I can substitute the V with E/B, therefore the E to M ratio would be E/B squared times R. J.J. Thomson could measure and calculate the strength of the electric field and the magnetic field he applied. He could also measure the radius of the path from the photograph, so he could calculate for the E/m ratio. If you remember, in the magnetism unit, this setup becomes very useful as mass spectrometers. Can you figure out what direction electric field has to be applied here in order for the cathode rays to go straight undeflected? In order for the cathode rays to go straight undeflected, the electric force and the magnetic force, they must be in opposite directions. So we can do V cross B, but because the cathode rays are negatively charged, so we have to flip the direction and get the downward. So magnetic force goes down, that means the electric force must go up. In order for the electric force on a negative charge to go upward, the electric field must go down. So the electric field in this region has to go down. For his work, J.J. Thomson was credited for the discovery of what we now know as electrons, because he was the first to measure the E/m ratio for electrons. He was also the first to suggest that a cathode ray particle was over 1,000 times smaller than a hydrogen atom, and he argued that these cathode ray particles were not ions, but constituents of atoms.